All right. So, all right. We're still getting things set up. Why is it not displaying? Oh, display off, of course. There we go. Hold on just a second. All right. One way or another, the quiz will work. I'm going to see if I can get my postdoc to bring us over some more bubble sheets because, you know, that's just how this day is going so far. All right. So let's start with where we are. We're looking at the syllabus / schedule. We are there, right? Friday, we're going to have time complexity, searching and sorting. More of that today. And then tonight we're going to have, or this afternoon, we're going to have a recursion lab. Yay. Yay. All right. I sometimes think I should run it like a gospel church and have everybody say amen. Everybody say amen? No? Ramen. There we go. For the pastafarians. All right. So let's go to, I'm working on the bubble sheets. Don't worry about it. Now, when we left our heroes, hold on. I'm going to try printing from here. I'm not sure I can. So this is, I'm going to show you the joy here of printing. More options, more options, more options. Yeah, I know, right? And now I can put in monochrome, and now I can put in 90. And now I can say print. All right, and okay, so are there any questions about what we covered last time? Anybody have a question about anything last time? Or you perfectly understand merge sorts and bubble sorts and selection sorts and all that? You could write them from memory, no doubt, every one of you, right? Yes.
Michael, can you go over selection sorts?
Yes. So let's go to C13. Okay, so here's the selection sort. So what we do, right, is we're constantly finding the minimum. So we find the minimum from 0 to 1, and we swap that into position 0. Then we find the minimum from 1 to the end, and we swap that into position 1. And then we find the minimum from 2 to the end and swap that into position 2. That's the basic idea, right? Okay, and so the way that looks in code is I go through the loop. First, I start at 0. I sort of guess that the minimum index is going to be I, but then I go through the remaining indexes from I plus 1 to the end, And if there is a different one, if there's one that's less than my minimum, then I update this index for the minimum. All right. So, all right. Does that answer your question? All right. So yes, Scott.
That's the only one that doesn't use recursion, right? All the
No,
others-
bubble sort does not use recursion either.
Okay.
Okay, so the two fast sorts use recursion. So we have the merge sort and the quick sort both use recursion. Let's go back to the quick sort. I mean, I covered that very briefly just as we were walking out the door. All right, I'm going to try to send Lucas a quiz form. You can watch me type things. All right. So let's talk about quick sorter again. All right. So the concept behind quick sorter, right, is if you want to think about this, is that we're going to pick a number. We're just going to pick a random value out of our list, and we're going to divide things into less than, equal to, and greater than. All right. Less than, equal to, and greater than. And what we're going to do is we're going to do that recursively on the less than pile and on the greater than pile. Okay, that's the concept. All right, so how do we do this? So first we have to have our bailout condition, of course, and the bailout condition for sorting is nice and easy. If you have a list of 1 or 0 things, it's sorted. If not, then I pick a random index from start to end, and I call that the pivot, and I get the pivot value from the array. And then I call this partition function, and the partition function is going to take everything less than this pivot value and sort it into the front of the array, and then return to me the index of where it ended up. And likewise, if I'm going to call with +1 so that I get, the equal to things in the middle. So I get I1, everything is going to be less than the pivot value. I2, everything is going to be less than or equal to the pivot value. Make sense? Right? And then with the way the partition function works is we're going to, we've got an array of things, and we're looking for things that are less than a certain value, and we want them at the front. So if they're already, if the thing at the front is already there, then we just keep moving the I1 forward, right, until it isn't true. And at the end, if the thing is already greater than or equal to the pivot value, to the pivot value that we passed in, we move that inwards. And then if they're both out of whack, right, if the I1 is greater than the pivot value, and I2 is less than or if I1 is greater than or equal to the pivot value and I2 is less than, then we can just swap them. And then finally, when those two things meet, the array will be partitioned. Does that make sense? Okay. So the mental picture that you should have for quicksort then is find pivot, partition, and then sort. Okay, make sense? And the mental picture that you should have for merge sort is find the midpoint, sort, then merge. Make sense? Question? True.
Go back to quick sorter.
Yeah. Yeah, so the partition function says, right? I mean, if you think about, just let's imagine you have an array. And let's say pivot value is equal to, say, 5. And then I have 1, 2, 3, 4, 5, 6, 7, 8. All right. So let's say I have something that's already sorted. What is this partition? This partition function should do nothing, right? So what I'm going to do is I'm going to start with I1 is going to point here, and I2 is going to point at the end. I'll just put a 2 there. 2 is going to be there. Okay, so what I'm going to do is I'm going to look at this position, at this 1, and say, is this position greater than or equal to the pivot value? I'm sorry, is this less than or equal? Is this less than the pivot value? Is 1 less than 5? And the answer is yes, it is. So what I'm going to do is I'm going to move this to here, right? Then I'm going to say, is it less than 5? And it is. So I'm going to move it again. Is it less than 5? Yes. Is it less than 5? Okay, now it is not. Now let's start with the 2, and let's so the 2 with the 2 we're going to do is we're going to look at the next one in. So is 8 greater than or equal to the pivot? Yes. So I move it in to here. And now I say, is 7 greater than or equal to the pivot? And again, the answer is yes. So I move it there. Hold on. Now I say, is 6 greater than or equal to the pivot? And I say yes. Okay, so I move it there. All right. And then I say, is 5 greater than or equal to the pivot? And the answer is yes. So I move it in. And now both 1 and, let's put a 3 there because 1 and 2 are both there, right? And my while loop says, while I1 is less than I2, we do this, right? And so this partitioned the array. It was already partitioned, but it figured out that it was. Now, assume, right, that instead I swap these two like this. Okay, and I start here and here. Okay, so I'm going to again go through this procedure where I move it along, and then it's eventually going to get to there, right? And now I'm going to take this other one, and I'm going to move it in, and it's eventually going to get to here, right? And now we've got this one. The I2 minus 1 is pointing to something less, and this is pointing to something greater than or equal to. So in that case, I swap them. So I put the 3 here and the 5 there. And then I proceed as before. And of course, it walks in. So that's how it partitions, right? It walks in from the ends. And whenever it finds both things are out of order, it swaps them. Sure.
So the last first example, when everything's already sorted, it both gets that 5. It still goes to that second else statement, but it's the same number. So
Well, no, it doesn't get to that else if statement because of this. Right? I1 less than I2. As long as I1 is less than I2, it can keep going. But as soon as they're equal, it's done. And any heuristic that I pick, right, like I say, always pick the middle or always pick the end, is going to fail for some particular arrangement of numbers. So the idea is we use a random number to prevent us from falling afoul of any particular arrangement. But that means that theoretically, if I picked all the wrong random numbers, I could wind up with an n squared time to search the array. In practice, that is so unlikely to occur that it doesn't happen. That is why I say when we talk about what's the speed of this array, at least in this class, the answer is n squared, is order n log n. Even though there is this pathological possibility of n squared, it almost never happens. Okay. Other classes may want you to say something different in this case. But what I want you to understand is this is going to give you order n log n performance. So that's the answer I want. Does that make sense? Okay, good.
But if we're doing the code notation, it would be n squared.
No, it should be n log n.
Okay.
That's I mean, that's the average case performance, right? It's not the worst case, but the worst case is so unlikely. It's not really worth considering, in my opinion. Okay. Yes.
With big O.
Yes.
Saying that, it would usually be, or also be 2 times in or 3 times in, but saying you'll never see it 2.
You should, yeah. Okay. So the question is, what about big O of 2n? And my statement last time was that is always wrong. Okay. If there's a coefficient in the front inside your big O, that violates the whole spirit of the big O. The big O is trying to get the asymptotic behavior with large values of n. All right. So we don't even want to see n squared plus n, really. I mean, what we want to see in that case is n squared, because at large n, that's the dominant thing. So when we look at big O, that's what we're looking for. We're looking for the asymptotic behavior, and we don't want the coefficients. Yes, Olivia. Yeah, big O is just a heuristic way. It's just a way of looking at our code to understand how it's going to scale, how it's going to change when we get very large values of some parameter that's important to us. In this case, the size of an array that we're sorting. So in this case, we can analyze the bubble sort and the selection sort, and we can see that they're order n squared. And we can look at the merge sort and the quick sort, and we can see that they're order n log n. And n log n grows much more slowly than n squared. So it doesn't matter how well we optimize a bubble sort. It's never going to compete with a merge sort, because it's fundamentally a broken algorithm, right? It's fundamentally doing things in a way that's too hard. So it doesn't matter how well I do that too hard thing, it's still too hard. No matter how efficient my company is for delivering ice to your house by hiring people to go chip it out of a lake and carry it on a truck, it's never going to actually compete with your own refrigerator, right? It's kind of the same thing. Any other questions? Yes,
Yeah,
Ding.
could you do like an example for merge sorts, like similar to what you did for quick sort just now?
What do you mean?
Like you were showing like how to.
Oh, okay. So, all right. So the question is, can I, do a little demo of merge sort the way I just did with the partition function? Okay, so that would be the merge step, I guess. And the way that would work is we're looking at this merge step at the end. So let's suppose I have 2 piles, and in pile 1 I have 1, 3, 1, 3, 5, 7. And then in pile 2, now the 2 piles have to be sorted, right? Because that's the concept of the merge sort. I sort the 2 things first. So I have 2 sorted piles, and I'm putting them together. And in this case, I'm going to have 4, 6, 8 in my second pile, let's say. So now I want to merge these. So what I'm going to do is I'm going to start a 3rd pile, and I'm going to look at the first number in each of my 2 initial piles, and I'm going to say, what's the smallest? And so I'm going to take that one and I'm going to put it here and then take it out of that pile. Now, which is smaller, 3 or 4? 3. So I'm going to put the 3 on the end of this pile and take it off the front of this one. And now what's smaller, 4 or 5? 4. So I'm going to put the 4 on here and take it off there. Next it'll be the 5. So I'll take it off here and put it there. Next is the 6. I'll take it there, put it there. 7. That pile is now empty. Okay, so at this point, I've exhausted this loop here where I said, while I1 is less than first and I2 is less than second, right? I had 2 piles essentially with at least 1 card in them, but now I've only got 1 pile left. So I'm going to go through my first one. Now my first pile is empty, so this loop will do nothing. And my second pile has got 1 card in it, so I'll stick that 1 card on the end. How's that? Amazing, right? All right. All right. So let me go back and just show you this again, because I want to make sure that this makes sense to you. So when I do, when I'm talking about n log n, and this applies both to the merge sort and the quick sort, right? What I'm going to do is on the first step of this merge sort, I'm going to do my two sorts, but don't think about that for the moment. So I'm going to do my two sorts, and then I'm going to do something to every element of the array, right? So, and then on the next step, I'm going to do my, for this, I'm going to call this twice, but that twice is going to cover the whole array. And so when I work on the whole array, I'm essentially going to work on the whole thing once. And then I'm going to divide the array again. And I'm essentially going to work on, you're going to have 4 calls, and each of them are going to cover a different piece of the array. But at the end, I'm going to cover the whole array, and I'm going to do work all across here. But the number of steps I do is going to be the log, because each time I'm taking half until I get down to 1. And so at the end, when I look at the amount of work that I'm doing, it's n times log n. Does that make sense? Does it not make sense? Are you like caught in the headlights ready to be shot? Yeah, I don't want your heads to nod at that one. No, seriously, is there a question? Does that make sense? Yes, Vanek.
So this is like the recursive part of the program.
Yeah, the recursive part is, so the recursive, this is the first recursion, this is the second recursion, right? If I'm looking at merge sort, the way it's going to work is I'm going to start with the whole array. I'm going to call sort, sort, sort. Then I'm going to come back up, call sort. Then I'm going to merge these two onto here. Then I'm going to go here and here and here. And then I'm going to merge these two up onto here. And now I'm going to merge these 4 up onto here, right? And then I'm going to go down this side. I'm going to do this one and this one and this one and so on. That's the way it plays out. Yeah, because every time I go into the call stack, right, I'm going to allocate more space. So let's see, I think I have this in my slides. Let me just check this point I want to make. Okay, oh yes, it's on here. Okay, so let's take a look at this slide. We have the merge sorter and the quick sorter. Okay, in both of these codes, the time is proportional to n log n to run. And they both use recursion. Quick sorter uses a random number. That's an important fact about quick sort. Okay. Also, you could say that, and I didn't put this on the slide, but merge sorter uses more memory, right? Quick sort does everything in place, but merge sorter has to allocate all these arrays. So you might just say, oh, well, quick sorter always wins. But quick sorter is not stable. What does that mean? It means that if I have equal values, right? If I have some subset of values that are equal according to my comparison criterion, then the quick sorter won't keep them equal. So think about a spreadsheet, right? So you have a spreadsheet and you ask it to sort by first name, right? And then you ask it to sort by last name. And kind of what you expect is that the sorting by the last name won't undo the sorting by the first name. That is, if I've got like 10 people named Green, people within Green will still be sorted by first name, okay? That will be true if you use a merge sort, but not if you use a quick sort, okay? So that's what it means by stable. The things that are the same according to how you're sorting can get shuffled around with a quick sort, but they won't with a merge sort. So which one you want at a given time is going to depend on your needs. Do you want to save memory? Then you want to if you want to save memory, you want a quick sort. Do you care about stability but not memory? Then you probably want a merge sort. Make sense? Okay. All right, so what if we're not sorting integers? right? I mean, integers are great and we love integers and they're easy to work with, but not everything is an integer, right? I just gave you an example, right, where we were sorting people in a database, right? And they had first and last names and we wanted to sort by that. How do we do that? So what we've got is this thing called we have this thing called a comparable interface. And what that's going to do is it's going to have a compare to method on the object. So anytime you look at like capital integer or capital string, those things are going to implement the interface comparable. And so what they're going to know, what that means is they're going to know how to compare to themselves. And any object can in principle do that as well. So what happens is, if I don't want to use the normal less than operations, I can say a dot compare to b. And if it's a capital integer or capital string, that will work, right? And this means the same as this. So it's kind of like I take the less than and I slide it to the right. I put a 0 at the end and a compare to in the middle, right? If you want to think about it that way. The other way you can think about this is subtracting b from both sides. A minus b is less than 0. So compare to is kind of like subtraction. And in fact, it can be implemented that way. It can be just a minus b. Okay, any questions about that? Okay, because this is going to be another thing that we can have quizzes on. What does this compare to function do? Here, I'm sorting with this. What happens, right? So you should be ready for that. And in this case, what I'm going to do in my show method is it's going to show what compare to does. So if I say, all right, so if I say 1 dot compare to 20, it's going to say -1. And I'm going to say 1 dot compare to 0, it's going to say 1. And 1 dot compare to 1 is going to be 0. So the idea is, right, when I'm looking at the result of compare to, I'm only interested in 3 things. Is it negative? Is it 0? Is it positive? Right? And I can implement it with negative. So if I said 1 minus 20, that would be -19, and that would be fine. Right? That would be a reasonable implementation of that. They chose to do something a little more sophisticated and always give me -1, 1, and 0, but you shouldn't count on that. Okay, so that's how compare to works. Now, how compare to works. Now let's look at how we would deal with that in, say, a merge sorter. So what changes in the merge sorter? Well, now I'm sorting an array of comparables instead of integers. So a comparable is in java.lang. That's where that interface is, and it has that single method compare to on it. So my bailout condition is, again, the same thing as it was. Oh, so as before, right, I have my helper method. And in my helper method, I put 0 to array.length to fill in the start and end methods for the merge sort. Then if end minus start is less than 2, I bail out because an array of 1 element is sorted already. Now I'm going to pick my midpoint using this formula. And then I'm going to sort my arrays from start to mid and from mid to end. And now I need to put them together. And this code is almost the same, but here is where it's different, right? This line where I'm comparing, I'm saying first I1 dot compare to second I2 is less than or equal to 0. Instead of saying I1 is less than or equal to 0, I now have this compare to function. And everything else is really the same. Okay, I just made that one little change. And now I have a sort routine where I can sort strings as well as integers. So in this case, I'm going to look at this. I'm going to have Java merge. Oh, come on. My computer needs coffee. Oh, sorry. Just try to give it enough work that it actually shows up, right? So this gives you an idea just how fast it is. I'm sorting 80,000 things with my, I didn't use merge sorter O. What am I doing? What am I doing? All right. And great, I'm out of power. Okay, so as you can see, right, what I did is I sorted integers and then I sorted strings and I used the same thing and it worked. The same piece of code and it worked. All right. Does that make sense? Are we good? Yes.
Brad, if the compare to is subtracting them, how is it doing strings like that?
Well, the string has a compare to method on it that the makers of Java implemented, and they made it return the 0 or -1 based on lexicographic order.
Compare to basically just determine like is it 1 or 0 or -1.
Yes,
And then it's
right. Compared to is using it's going to be less than is negative, equal to is 0, and greater than is positive. Is the way it's going to work out. Okay. I'm going to give you the quiz now. And for those of you who don't have bubble sheets, just write your answer on the quiz itself along with your name. And I guess I will have to bubble something in for you. That's just the way it's got to work today.